Hi guys, nice to meet you. First of all, thank you for click on my live stream and watching. So today I want to learn about computer science fundamentals. So we have I have one course on Brilliant, and it's super cool. So we go to the meaning of computer science fundamental for this course. In this course, uh, um, will wrap your mind around computational thinking from everyday tasks to algorithms. Learn the key ideas of computer science with this interactive course. No coding required. This course is ideal for high school or college student who wants to learn the fundamentals, or an early professional who wants to strengthen their knowledge or core computer science concepts. Whether you are exploring computer science for the first time or looking to deepen your understanding, this course will allow you to develop the problem-solving techniques you need to think like a computer scientist. Following li- librarians, cooks, and majors to see how computer science problem-solving techniques affect their daily lives. Get hands on with a few specific algorithms and learn the general principles demonstrated by these algorithms. So, topics covered: binary search, bu- binary search. Okay, so far so good. Binary search,
Brute force search.
a brute force search, uh, concurrency,
Concurrency.
concurrency, decision trees, graph abstractions, greedy algorithm, indexing,
Indexing.
indexing, indexing, in interface, and
Parallelism.
par- parallelism, programming, programming. So today we have mm, tools of computer science, computation problem solving, algorithm, algorithmic thinking. So today with tab 1, where I will learn about tools of computer science. So computer science helps you understand the world around you. First, I will go to the first topic here, making decisions. Making the wrong decisions. I think that I need to change my face to here. Okay, it's look cool right now. So making the wrong decisions. As powerful as decision trees are, they do end up having important limits. Uh, so as trees are, they do end up having important limits. Okay, which phase will the computer land on? Land on.
Land on.
Land on if you use it to identify this blonde hair face. Brown hair. So, oh my god, I don't understand anything. Uh, okay. So brown hair. Brown hair. No, he is blonde. He doesn't have brown hair. So is the false black hair? No, he doesn't have black hair. So it's for. We need to go. Uh, brown hair. Brown. Is it not brown, right? Doesn't it? Isn't it? Like it is not brown hair, isn't it? Because I see it's like yellow. Mm, here, not quite. So is here. I think he has like a yellow hair. So the first statement is wrong. So we need to move to black hair. And yeah, he doesn't have black hair either. So this the second statement is wrong either. So I think uh, false and go to blue. Sure. Easy, guys. Easy. Super easy. Explanation. The new face doesn't have brown hair, so the computer follows the no path for the first questions. Similarly. Similarly, the face doesn't have black hair, so the computer follows the no path for the second question. This leads to the last face on the right. Choose, choose, choose. The decision tree didn't do a good job of recognizing. Recognizing. The decision tree didn't do a good job of recognizing this recognizing recognizing this face. They are about as different as can be, but the computer decided they are similar. Okay, quite good. So computers can make mistakes because they rely on decision trees designed with limited information. Mm-hmm. Okay, quite good though. Let me see. The subject is obviously a chihuahua in a turtleneck. In this case, the decision tree is focusing on the placement of dark circles on a tank background. If the tree is
calibrated,
if the tree is calibrated to identify dark brights, it may be fooled fooled by a moving decision trees don't see face or dogs. They only consider features with instruction them to focus. Oh my god, what does it mean? I still don't understand. What the heck is it? Uh, uh, Computers can make mistakes because they rely on decision trees designed with limited information. Okay, it's true. Like computers, I th I think that computers, if we like provide enough information for computer can a computer will rely on that decision and make the tree designs. The more information you put, the more computer figured out. The subject is obviously a tutorial in it. In this case, the decision tree is focusing on the placement of dark circle on tank background. The tree calibrated to identify dog breast.
Dog breeds.
Dog breeds. It may be fluid by a muffin.
Muffin.
Muffin. Or the decision trees doesn't. Oh, so like now, we have computer and we are we calibrate
Calibrated.
calibrated. We have computer. I have computer, and my computer need to identify dog breeds. So it may be fooled by a muffin. This is a muffin. Like, yeah, our my computer is the fooled by a muffin. Decision trees don't see face or dogs. They only consider features we instruct them to focus on. So far so good? Understand? So if you pay attention to the news, you'll see real world examples of this kind of failure. Failure.
Failure.
Failure. Computer decision making in cars can lead to accidents if objects on the road are misidentified. Understand? Quite good. So far so good. And many facial
Facial.
facial recognition recognition system don't work well for people with darker skin, as they were designed with pictures that skew too heavily toward lighter skin tones. Some facial recognition systems used by police have resulted in the wrong person being arrested. Automated decision making can get things wrong in unexpected ways. Oh, I understand a little bit about these tools of computer science. Review and reflect. Review and reflect. Computers are good making a lot of decisions quickly, right? It's good. Computers are good at making lot of decisions quickly and tirelessly, but nothing guarantees that they will make the right decision. It's true. But nowadays we are more and more modern, so I believe that when if we put a lot of provide a good statement, and so that's up to us humans. In the rest of this course, we'll learn more about how computers work and they can do. Finish lesson. So far so good. Congrats on your 0 day stack.
Congrats.
Congrats on your 0 day stack. Streak.
Streak.
Continue. So far so good. How likely are you to recommend Brilliant to a friend or colleague? Look, learn system. Like, is 10 extremely likely? We have already done making decision topic. So now we go to writing programs. So if you want a computer to interact with the world, you're going to need to write a program. So nowadays we are more than about AI, artificial intelligence. So if you want a computer interact, AI chip interact with the world, you are going to need to write program. Cool. Writing programs. In this lesson, you'll learn how to write simple programs starting with basic steps. You'll create programs that accomplish more challenging tasks. The techniques you are about to learn will introduce you to the tools, the tools
Tools.
the tools that are used in computer science all the time. Giving instructions. Congratulations, you've been hired. Hired? Hired.
Hi- hired.
As a new employee of Amazon. Super cool. For your new job, you'll learn how to write programs that control the eye of Amazon to deliver bales
Bales.
bales of hay
Hay.
bales of hay to the barns
Barns.
barns of Jeff Bezos, the richest horse in the world. Okay, so I need to learn how to write programs that control the eye of Amazon to delivery bales of hay to the barns of Jeff Bezos, the richest horse. Greetings, new employee of Amazon. Meet the eye of Amazon, a drone
Drone.
that delivers bales of hay to many barns of our great leader, director Jeff Bezos. Welcome to your first eye of Amazon program. Unfortunately, there's a little problem. The current program causes the drone to crash. Hit the run code button to see yourself. Run code. Here, here, go, and go. Ah, super easy. So we have a little bit problem here about our codes. So continue. Let's fix this problem. Drag,
Drag.
drag the blocks from the top row to the bottom one to guide the drone to the being born. Uh, how to say? Hard symbol 6. If you add an extra block, get rid of it by drag it off. Here, here, here. No, we need we need five. We need 5 blocks. Oh my god, it's tricky. It's tricky. It's tricky. Oh, it's tricky. It's starting to tricky me. It needs it need it needs at least 5 blocks. So if I like give it like it's still it's tricky. It's tricky. No. Here le No. It's tricky. It's tricky. It's not easy though. Here. Go go up. No, it's still wrong. What I need to do right now is how to use 5 blocks, and it's come to. Oh my god, it's not easy then. Let me see. I need to go to the right, uh, go up, go to the right, and go up. We run code. Oh yeah, we can guess just 5 correct. Oh, so easy though. Computer scientists write the instructions that computers execute. Computer scientists write instruction that computer execute. So yeah, for your next training task, you'll write another program for the eye of Amazon. Drag the command blocks from the top row down to the bottom to write a program that guides the drone to the red barns. Hard simple 3. So go up, go up, go to the right, go to the right hand, go up, go to the right hand. We are here. Go to the right hand, and it's kind of really easy though. Oh, we need to one more. Congratulations, it's super easy. In the last 2 programs, you wrote sets of instructions to navigate the drone to where you wanted it to go. Writing a program is about getting the computer to execute a series of instructions. Why these programs might seem simple, learning how to tell the computer that what to do is a fundamental part of computer science. Yeah, so like now we just have like a computer and we need to write a program. In another words, we need to provide computer instruction information to give our to give my computer understand. Yeah, okay. A program is a set of instructions for the computer to execute. Understand? Limited instructions. The programs we can write for the role are a product of the instruction we can give. So far, we have only had access to directional instruction with these blocks. The drone can still reach the pink barn. 6. You can figure out how. So which of the other barns are reachable with the available commands? So here, let me see. Let me see limit instruction. The programs we can write for the role are a product of the instruction we can give. So far we have only had access to directional instruction with these blocks. The drone can still reach the pink barn. go up, go to the right hand, we are here, go up, we are here, go up, go to the right hand, we are here, or maybe, oh, we don't have the left hand narrow, we don't have the left hand narrow, so our limited our limit is couldn't go to the second, the blue house. So, and we don't have go down narrow too either. So we just have only which of other bands are reasonable with just six. Mm. Which of neither band 2 nor band neither band neither
Neither barn number 22 nor barn number 44.
is true. It's easy. So explain. If you had all four different instructions, it would be possible to reach both the blue barn has symbol 2 and the green barn has symbol 4. Yeah, if we have four different instructions like go up, go to the right, go to the left, go down, so we can reach every house here in the picture. But however, you only have two different instructions, north and east, despite the fact that blue barn 2 is due north and the green barn 4 is due east.
East.
The obstacles in the way prevent you from reaching either band with the limited instruction you were given. Because of the limited instructions, the drone is unable to reach either blue band 2 or green band 4. Adding to the available instruction increase the power of the programs that you can write. Okay, it's true. Navigate the drone to the yellow barn 1. We go. I think that if we want to go to the yellow, we go to the right hand. We go up to 2 blocks, and we go to the right hand 2 blocks. Run code. It's super easy though. The yellow barn first is reachable with this program. Here is the same map as in the last puzzle.
Puzzle.
The last puzzle, but the drone's initial location is one square further to the west. How many barns can the drone reach from this new starting point? So as we see, when we use full 5 blocks, we when we use full 5 blocks, we when we use like 5 blocks, we come to yellow band. But when we location is one more square further to the west, so uh, definitely yellow now. Yellow house. We unable to reach a yellow house. How many pounds can the drone reach from this new starting point? So like R6, we cancel R6 answer. No. Definitely we can go to blue house. So we cancel 0 answer. And the six the purple house is the same with yellow house. So because yeah, it, as you see that you will see that the purple house will the same with yellow house that need 6 blocks. So definitely, and up to this house, 3 house, third house, fourth house, and fifth house, just one. Easy, you see, easy. Thinking is all thinking is all thinking. Only one barn is reachable blue barn, two and all other barns take at least 6 steps to reach, but there are only 5 available instruction steps for the programs. Here is the program that reach blue. Okay, understand? When writing programs, you need to learn how to achieve your goals with the commands available to you. The more instruction that you can provide for computer, the more that you are able to accomplish with your programs. Programs are limited by the commands available. Repetition. So far, your programs have been relatively simple. The drone has executed as a sequence of instruction, one instruction at a time. Computer programs get more interesting when you can repeat instruction multiple times. The program below contains the repeat instruction, which allows you to repeat commands when the program executes. The repeat instruction, it follows the arrow to the arrow
arrow,
the arrow, not narrow, and repeats the early instruction until the counter reaches 0. What? The program below contains the repeat instruction, which allows you to repeat commands when the program executes. The repeat instruction, it follows the arrow and repeats the early instruction until. Understand? So far so good. I understand this meaning. Quite easy for me. The program above used the repeat instruction to move the drone east 5 times without the new repetition instruction. How many basic direction no instruction would your drone need to get ping pong? 1 2 1 2 3 4 5 5. Easy. The drone goes east 5 times, which can be done without the repetition instruction. However, the repetition instruction lets us simplify the code to only 4 steps to get the ping pong 6. With repetition, we can write with repetition, we can write programs that accomplish more tasks with fewer instruction call. To add a repeat instruction, drag in it one the program and then point the arrow to the instruction you want to repeat. Find the pattern that you can repeat to guide the drone to ping pong 6. We are now here. We need to go up 2 blocks and go to the left 2 blocks. So easy, super easy. Oh, come on. It's super easy. I think so. It's not easy at all. It's not easy. Oh my god. So. It's not easy, guys. Uh, what I need to do right now is repetition. Go to the right hand. We we just have 5 blocks. Mm. It's hard, right? I know it. Yeah. Oh my god, it's the part is not easy though, guys. We are here. Hmm. Oh, the house 6, not the house ones. Oh my god. Oh, so we can repetition like this. Uh-huh. It's hard for me. Oh, we can do both. Oh my god, it's so easy. It's so super easy. Here, I just need the 4 steps. Okay, does it cool? Super cool. I need just 4 steps and I can here. Easy, right? By recognizing by recognizing a pattern that we can repeat, we are able to reach the ping pong 6. What we used to need 6 comments for we can now do it for? Yeah, definitely. Using repetition, we can write simple programs to accomplish more complicated tasks. Repetition is a powerful tool in computer science that lets you write programs that can make use of limited space. Recognizing, oh my god, error.
recognizing,
Recognizing patterns. As the program of the Eye of Amazon, you'll want to figure out how to write programs to guide the drone to all the bands. Let's practice. Band 4. So band 4. It's hard for me now, so we need to step here. Okay, it's quite easy. Go to the right hand here, we are here. Go up, go to the right hand, we are here. Go to the right hand, we are here. Go to the right hand, we are here. Oh, we have repetition 3. So if we want to do it, we just do. It's so easy when we just do 4 steps. Oh my god, here. It's easy. You might have noticed that there were multiple programs that solved the puzzle. The difference comes in how the step move is 4 times is implemented. One way use the trick that you saw early to move is 4 step with 3 instructions. Alternatively, you could move it once and repeat that process 3 more times. This lets you move it 4 steps with only 2 instructions. In this task, we found 2 different sets of instructions to guide the drone to band 4. In computer science, there are often multiple ways to write programs that accomplish the same task. For your final training task, guide the drone to purple pen 5. I remember here. Go to the right. With repetition 2, we are here. We are here. We are here. So easy. Here we have the programs to guide the drone. Do you think they will both guide the drone to the same destination? Yes, that's right. Although these are different programs, they both serve to guide the drone to the same spot on the map. Both programs use repetition to follow patterns that reach the destination. Let's see how this is done. So the first solution use the right go to the right arrow and go down arrow pattern illustrated below here, and with repetition one more time. The second solution use the two to to the arrow go to the right and one arrow go to the left. Okay. In each of these programs, there were multiple ways to guide the drone to learn to the burn. As you'll see in computer science, there are often multiple ways to write a program that accomplishes one goal. To recognizing patterns and using the repetition block, we can create more solutions that we could otherwise. In computer science, there are often multiple ways to build programs. Okay, we have already done review and reflect this topic. Review and reflect. These little programs have only presented the smallest
glimpse
of what you can do with your programs, but you'll encounter many more possibilities in what follows. We're done. You are on a one day streak. You can make it to 3 days in a row. People with 3 day streak are 17 multiples more likely to complete a course. How likely are you to recommend Brilliant to a friend or colleagues? 10. How do you plan to use computer science in your life? To advance, no, to prepare. To advance in my, to like make artificial intelligence. AI, machine, how to machine learning. What is your comfort? What is your comfort level with computer science? Why are you interested in learning more about computer science? Is modern the future of human? Searching for solutions. Sometimes the right way to solve a computational problem is by brutal searching for solution. In this lesson, you'll look at a class puzzle about 7 bridges and develop a system approach to solve this puzzle. Although it will seem impractical, this type of approach leverages the core strength of computers. So, like quickly and tirelessly doing many tasks. The bridges of Seven Kingdoms Bridge, the Russian city of Kazan lies about 30 kilometers north for Poland, where their budget matters basic scene. What does it mean? Poland. Okay. The city has a the city has a famous place in mathematical history dating back to the 18th century when the city was named and has several bridges connecting to two river islands in the heart of city. This arrangement of seven bridges lead people to ask a simple yes or no question. Could you start anywhere in city and cross every could you start anywhere in city and cross every bridges exactly once? No swimming allowed. I don't understand. This arrangement could you start anywhere in city and cross every bridge exactly once? No swimming allowed. Oh, it's easy to attempt the puzzle and get stuck. Here is a path through the city that gets stuck after crossing four bridges. Okay, so for easy to understand that you need to cross every bridge exactly once. So what exactly one way like that. This is now you just cross four bridges and you stuck and you need to go again and you need to repetition this bridges. So is the do you think that is possible to cross every bridge exactly once? Just give us let me see. One, two, one, 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 two, one, two, one, two, mm, three, four, five, six, one, two, three, four, one, 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 two, three. Oh my God, how can I do it? One, two, three, four, one is hard. Just fine. No, impossible. This was the
suspicion,
suspicion. This was the suspicion of many residents.
residents,
Residents when they try and fail to come up with a solution, but for a long time no one could give a convincing argument for why they couldn't achieve this goal. That's where the interest in computer science enters the picture. Really? So can you find a path that crosses bridges before getting stuck? Remember, you are not allowed to cross any bridges twice. No. Really? Oh my god. We can? So in the end of this animation, you are on the north and you can get the remain bridge, bridge in the middle that concept to islands. There are several ways to crossing 6 bridges before getting stuck. Here's one. Oh, if 6 I can do it. It's easy to get 6. I think that about 7. If about 7 we couldn't, but for 6 we can. Even if you even if you are allowed to start or end anywhere you start, you can't cross every bridge exactly one. You'll get stuck after almost 6 bridges. Let's turn the problem on its head to make sure we understand it. If you're allowed to start anywhere but can't cross any single bridge twice, that what is the fewest number of bridges you can cross before get stuck? 4. 3. Oh my god, 3. 1, 2, 1, 2, 3. Okay, 1, 2, 3 here. I see. You can get stuck after 3 bridges by starting on the S Island, crossing to the north bank, Aston Islands, crossing to the north bank, then crossing to the Central Islands, and then finally return to the north bank. It's tricky to show that you can never get stuck after crossing 2 bridges. One way to show this is just to try every way of crossing 2 bridges and see that you're never stuck. It's identifiably possible to get stuck after crossing just 3 bridges. Yes. Now that we've gotten familiar with the problem's setup, let's turn to the main problem, finding a way to definitely show that these 7 bridges cannot all be crossed without crossing any ties. System Systematic explorations. A useful problem-solving technique is to list all the possible solutions and then check each solution. We might we might try to imagine a system sys-
Systematic.
we might try to imagine a systematic way to explore the city, a way to ensure that we will try to every possible way of crossing the bridges and can be sure we didn't miss anything. This systematic exploration is a general problem.
Systematic exploration.
Systematic exploration, a useful problem-solving technique, is to list all the possible solutions and then check each solution. We might try to imagine a systematic way to explore the city, a way to ensure that we will try every possible way to crossing the bridges. This semantic exploration is general problem-solving technique and In the case of the bridges of we can in the case of the bridges we can number the 7 bridges. Uh, any way of any way of crossing the 7 bridges can be described as sequence of number. For example, a sequence of number that starting with 2, 3, 6 would correspond to a path that starts by crossing bridge 2 first, followed by bridge 3, and then going to bridge 6. Okay, a C1 a sequence 3, 2, 1, 6, 4, 5, 7 is not a solution for the problem of the grid. After crossing uh, bridge 3, then bridge 2, and then bridge 1, there is no way to reach bridge 6. Okay? So before approaching the full problem, let's first focus on just bridge 256. If is the C1256 a valid solution to no, because we can just do just 2 and 5. After crossing bridges 2 and 5, you can't reach bridge 6. How about the C1 here? No. Right, after crossing bridges 2 and 6, you can't reach bridge 5. Here is very simple permutation. Permutation. Here is very simple permutation of these bridge 3 bridges. Are any of them valid solution to bridge crossing problem? Nope. It's super easy. By checking every possible answer and finding none that are valid, we will find the answer to the 3-bridge problem. There is no such path. Solving this puzzle for 3 bridges is fundamentally the same as solving with 7. So brute force solution to problems can be required checking a lot of solutions. In the 3 bridges version, we had to check 6 different candidate solutions. We should investigate if it is even
feasible
for us to enumerate
enumerate
and check are the permutation for 7 bridges. How many candidate solution would we need to check for 7 bridges problem? What? A brute force solution to problems can require checking a lot of solutions. In the 3 bridges version, we had to check 6 different candidate solutions. We should investigate if it even feasible for us to enumerate and check our permut. It's like the numbers of permutation
Permutations.
Oh, permutation. So it's about like 7 plus 6 plus, let me see. It's about 7 plus 6 plus 5 plus, no, 7, how to say? Let me see. Multiple. Multi. Yeah, 7, multi 6, multi 5, multi 4, multi 3, multi 2, multi 1, 5. 5,000. We can now roll up. We can now roll up ourselves and start working our way down that list. Well, okay, these 5,040 candidate solutions are going to take us a while. How fast would you expect it to take a computer? Less than a second. A modern computer is easily able to perform millions of candidate checks every second. This would take a few milliseconds. This makes this approach every computationally reasonable, at least for. In fact, we can go through every option right now. Oh my god, see? In fact, we can go through every option right now. See? It's super fast when we go to like the compu our my my computer right now are checking like solutions. How can get 7. It's super cool. 2006 study of determined that city has 446 bridges. It would be interesting to see if we can solve this crossing problem in the same way. We will start running this program and it still hasn't found any valid path after an hour or so, and it's still running. That what we can conclude. We've, if the program hasn't finished running, it hasn't finished going through the list, it will eventually go through every single candidate on that list, and we will be able to conclusively decide at that point whether this problem has a solution or not. Okay, understand? Because this problem will eventually go through all the solution, it will eventually be able to decide whether or not has such a work. Let's figure out how long it will take. Imagine that computer can take 1 million different permutations of bridges every second. If we use the same brute force approach to see whether like 445 bridges can be crossed once without leaving any rows, how long it would take. More time than is left before the predict hard death of universe. an hours, more time than. I don't understand this. Really? Like if we use the same Brute Fox approach to see whether for 146 bridges in Brazil can be crossed once without leaving any roadways, how long it would take? More time than is left before the predict hard death for universe. Oh my god. So one way to estimate 446 permutation is to know it is greater than. Here. A very big number. The hard death of universe is estimated to happen in around oh my god years. Every year there are around 30 million seconds that less than 100 million or a second we can check million combination. Oh my god, it's it's super hard. The number of candidate solution for the bridges is so enormously giant, giant, giant,
gigantic,
gigantic. That is hard to wrap out my around it. There are more candidate solution is this to this problem than practice score in the universe. Even each if each practice score was itself an entire sub-universe with the same amount of practice score, there still would be
vastly,
vastly. Oh my god, so sorry. I'm sorry. Vastly more candidate solution than practice score in our sub-university.
theoretically,
Theoretically, there are only a limited number of ways to order, so programs that takes each one by one will eventually finish, but that theory isn't helpful for anyone in this universe. It might as well never finish. This is a fundamental problem with brute force problem solving. It sometimes requires checking far too many solutions to practice. Even if it feels unsatisfying, brute force is still the best way we know to find an ideal solution for many important puzzles in computer science. Maybe that's because there isn't any better way, but maybe that's because there is a better way and we just haven't thought of it yet. Super cool. However, for this problem, we have developed techniques that are much faster than brute force. We'll see how much better in the next lesson. So review and reflect. Solving problem with brute force is an important tool in computer science toolbox. It works especially well when the set of candidate solutions is small, as in historic. For many problems in computer science, it is still the only solution we know of. However, brute force problem solving gets a lot of harder when the solution get only a little bit more complex. Yeah, we have Done. Let me see. Let me see. Oh my god. Computer science super hard, not easy. Yeah, what? I have done this before. Oh, brilliant have a problem. I have done tours of computer science. Oh my god, making a decision now. We're wrong. Oh my god, modern computers can accomplish incredible things. They can play chess, the right cards, and diagnose disease, but whatever an application it break down to small question. Oh my, what is computing? Input output computing is the act of taking an input processing it and producing an output. In facial recognition, a computer may get a camera image as input, perform a sequence of steps, and produce an identifying description as output. Our first example breaks down the process of facial recognition into sequence of simple decision. A decision tree is a sequence of yes/no questions that help computer decide what to output. So, like just like reading a flow chart, the computer starts at the top of the decision tree and answers each question based on its input until it gets to the bottom. So, with this decision tree, what's the first question computer will ask of any phase? Yeah, do they have bread? Definitely. Here's how the computer steps through the decision tree when the input phase has no breath, has long white hair and no glass, and is not smiling breath. No. Brown hair. No. Smiling. No. There are one more questions. So the computer decides the face must be on the far right of this decision tree. Decision trees. What word the computer output if the presented with a forming face with short brows, hair and glasses, and no breath? Form face with brown hair, no breath, is font. Brown hair. We have brown hair is true and glasses is to just check. It's easy, right? What was the computer output of presented with a smiling face with blonde hair, fonts, no bread, fonts, brown hair, fonts, smiling, choose, blue hair, fawns, long hair, fawns, black hair, fawns. Here. Here's how the computer steps through the decision tree is this last example. Yeah, we understand. Now that you've seen how face recognition decision trees work, it's time to try building one from scratch. Creating decision trees. Imagine. Imagine that you want to make a decision tree that can distinguish these four faces. The computer has a camera that can detect glass, hair, color, and open mouths. If you want the root of the decision tree to split the face into two groups, which question were at first? Do they have black hair? Two groups of two. None of them will work. Black hair. Okay, so good. Two of them have black hair and two of them have no black hair. Understand? The first question is your decision tree splits splits the face into distinct group. Okay? What is a single question that you could ask of both remain groups to narrow down to single face? Do they have bed? The first question in your decision tree split the face into the first question in your decision tree splits the face into distinct groups. What a simple question that you could ask of both remain groups to narrow down. None of them will work. Because none of them will work. Like, do they have bread? Just one him have bread, but both of them. On another hand, both of these people doesn't have bread. The second, are they wearing hat? Yes, so explanation. None of these single questions will work for both groups. In the group on the right, the one without black hair glasses is the only person that distinguishes between the two faces. In group on the left, the question, do they have a bed and are they wearing a hat? Both work both work to distinguish the face, but those two questions don't work in the other group. No single feature can distinguish both groups of two faces. However, you can make a decision tree that distinguished
distinguishes,
dis- distinguishes all four faces by asking a different follow-up question based on the answer to the first question. So this ability to ask different questions depending on the answer to previous question make a decision tree quite powerful. So black hair, no or yes, red, no or yes, glasses, no or yes, continue. So far so good. Mm. Mm. Oh my god, we have done chapter complete. Wow. Oh my god, it's super nice to meet you guys. Nice to meet you guys. See you later. Thank you for watching me. Bye.